In this section, we're going to look at null spaces, column spaces, and linear transformations. So those terms we've heard all before. We saw those in Chapter 2, null space, column space, and a linear transformation. So it should be no surprise that in this section, we're going back to Rn. So we're going to travel back to the vector space and just focus on Rn for a while. In the next, in a couple sections from now, we'll see why we focus so much more on Rn, and we'll see some analogies to those other vector spaces. But for right now, going back to Rn. Now remember, Rn is the set of all vectors with n entries. Now, if you recall from Chapter 2, a transformation simply means a mapping from one set to another. So we're going to take a mapping from one vector space to another. In particular, we're going to focus on matrix transformations. All right? And a matrix transformation is a transformation defined by a matrix multiplication. So what it's going to do is it's going to take vectors from R to some power, so some vector space. We're going to multiply those by matrix A on the left, and we're going to get out vectors from possibly a different vector space. So we're going to transform the vector X into vector B by multiplying by A. So any matrix can be thought of as a matrix transformation. Now, what we're going to focus on first is the concept of the null space. We've seen this before. The null space of a matrix is the set of all solutions to the homogeneous equation AX equals 0. Now, a better way to put that is that the null space is the set of vectors which get sent to 0. And when I say 0, I'm saying the 0 vector. All right? So it's the set of all vectors. When you multiply them by A, you get out 0. And we denote that by NUL of A. Again, this should be a refresher for what we've done previously. Now it turns out if A is an m by n matrix, so if A has m rows and n columns, then the null space of A is going to be a subspace of Rn. Now we're going to show that this is true. All right, we're going to prove that this is a true statement, that if a matrix is an m by n matrix, that the null space has to be a subspace. Okay? So this is what we did in the previous section. We dealt with subspaces. And if you remember in the previous section, what we needed to show were three facts. We needed to show that the 0 vector was in the set. We needed to show that the set was closed under addition. And we needed to show that the set was closed under scalar multiplication. All right? So what we're going to do is we're looking at solutions to this equation. So I'm saying solutions to this equation are the null space. So the set of all solutions is the null space. So we're going to take eventually arbitrary vectors and we'll call them x and y vectors in Rn, which are in the null space. And we hope to show that under vector addition we're closed, under scalar multiplication we're closed, and that the 0 vector is in the set. But before I do, I just wanted to talk about why Rn. Remember, our matrix A had m rows and n columns. Well, if it has n columns, then when you multiply times a vector, that vector ought to have n rows. So the number of entries in vector x has to match up with the number of columns in matrix A. So that's why Rn, all these vectors are coming out of Rn. All right. So let's ask ourselves those three questions. First off, is the zero vector a solution to this equation? So all we have to do is take A and multiply it times the zero vector. Let's go ahead. I'll get back to basic math here. So multiply it times the zero vector. And notice that what you're doing is that each row of A is becoming a linear combination with all coefficients being zero. So if you actually went out and multiplied anything times the zero vector, you will in fact get out a zero vector. All right? So what's this mean? Well, in short, this means that the zero vector is in the null space. So writing that down, the zero vector is in fact in the null space of A. There you go. Since A times 0 gives you the zero vector, that means this zero vector over here is in the null space. Now, that's one point to show that something's a subspace. The other point we need is the sum of true arbitrary vectors in the null space also in the null space? So what we're going to do is we're going to take two arbitrary vectors. And obviously I'm using x and y because I'm saying those are my arbitrary vectors, which are in my null space. So we're going to take that and we're going to look at this sum. Now, how do we show that this sum is in the null space? We simply multiply by our matrix A. That matrix A times vector x plus y. Well, because of the properties of matrix multiplication, let me scroll down just a bit. Because of the properties of matrix multiplication, I can distribute the matrix to be multiplied times x and to be multiplied times y. Now, since x was in the null space, a times x is 0, specifically the zero vector. And since y is in the null space, a times y also has to give us the zero vector. Anytime you add two zero vectors, you get the zero vector. And so what that line shows us is that, is that the sum of two vectors that started out in the null space is in the null space. All right? Therefore, we are closed under addition. Remember, closed under addition means that if you add two vectors, that sum also has to be in the null space, or that our set in general. Now, what's the third property? The third property is we need to be closed under scalar multiplication. So what we need to do is we need to take an arbitrary vector, we'll call it x, and we need to multiply it by a scalar, and we need to see if an arbitrary scalar times a vector will also be in the null space. This one, all we have to do is multiply by a. Again, because of the properties of matrix multiplication, what I can do is I can take the c out front. I can say, Well, though I can reorder that scalar. I can drag that scalar out in front of this and multiply the a times the x before the scalar. So that's because of the properties of scalar commutativity and the associativity properties. And what's going to happen, since x is in the null space, a times x must give you the 0 vector. All right. Now, anytime you take a scalar times the 0 vector, you're just going to get out the 0 vector. All right. And so what this shows us is that whenever you take a scalar times a vector, if that vector was in the null space, scalar times the vector is also in the null space. All right. So that's what we mean when we say closed under scalar multiplication. So because of these three properties, that 0 vector is in the null space is closed under addition, and the null space is closed under scalar multiplication, we can come to the conclusion that any null space is a subspace of Rn for the appropriate dimensions, for the appropriate value of n. Okay, so that's it. That proves that no matter what A is, A, the null space of A is a subspace of Rn. So let's refresh our memories and go back and find some null spaces. Okay, we're going to find the null space of this matrix. 2, 3, 6 as the first row, 1, 1, 1 as the second row. So it's a 2 by 3 matrix. And we're going to look for the null space. If you remember how to do this, push pause on the video and try it yourself. If you don't, we get about 5 seconds and then we'll go through it. All right, so hopefully you went ahead and did that, if you could remember. And so we go back, let's erase this proof for just a second. Remember, the null space is all solutions to AX equals 0. So it's all solution to the homogeneous equation here. And therefore, what I want to do is I want to solve this. Now, what we do in order to solve a matrix equation is we either put it as an augmented matrix. In this case, we really don't need to use the augmented because the column to the right, the rightmost column of the augmented matrix is all going to be zeros anyways. So we can just put the matrix A into our calculator and go ahead and row reduce matrix A. Now, if you don't remember how to get to the matrix menu, second, and then this button here, matrix. If you don't have your matrix A already set up, you scroll over to edit. We want a 2 by 3 matrix, 2 rows, 3 columns. Remember, the first row is 2, 3, 6. The second row is 1, 1, 1. So once you get that input, all we have to do is go back to the home screen, ask our calculator to put this into row reduced echelon form, And what you do for that is you go into the Math menu, scroll all the way down or all the way up until you get to the letter B. So we're going to go row reduced echelon form, and then row reduced echelon form of my matrix A. Whoops. And the row reduced echelon form of the matrix A is 1, 0, negative 3, 0, 1, 4. Now remember, A was not the augmented matrix. A was the coefficient matrix. So remember, we're solving this equation. So if we have a row-reduced echelon form, let me write this out. If our row-reduced echelon form of A looks like 1, 0, negative 3, 0, 1, 4. Remember, the augmented matrix will have a column of zeros over here to the right. So the general solution to that would be that x1, again, I'm thinking of x, my vector x, as having 3 entries called x1, x2, x3. x1 minus x3 equal to 0, minus 3x3, excuse me, should be equal to 0. You should have x2 plus 4x3 is equal to 0. And then my x3 is a free variable. So general solution is that. Nothing's wanting me to click today. That's all right. All right, so that's our general solution. Most times we've been rewriting that. At first equation, we'd write x1 is equal to 3x3. That second equation, we'd write x2 is equal to negative 4x3, and x3 is equal to free. So it's a free variable. So the null space of our matrix A is going to be the set which includes all vectors that, first off, we know we have to have 3 entries. So they're going to look like all vectors of the form 3, negative 4, 1 multiplied times some constant x3 such that x3 is some real number. Okay. Did I forget that? No. There we go. So the null space is all vectors of this form. 3, negative 4, 1 multiplied times any real number such that that happens. So those are the things that all get sent to the 0 vector. Anything that looks like a scalar times 3, negative 4, 1. All right? So I want you to do another example. I want you to push pause and try this example. Find the null space for this matrix. Use the same calculation technique we did before. Right, so hopefully you went ahead and did that. Now again, what we're doing is we are solving this homogeneous equation, ax equals 0. We have a 3 by 3 matrix that we're starting with, but remember, we're going to start with the matrix A, which is going to be the coefficient matrix, and we're going to have a column of zeros to the right if we had an augmented matrix. So once again, we're going to go to our calculator in the matrix menu. Now what I did is I chose to put this in matrix B. Doesn't matter which matrix area you plug it in. There's lots of choices. So let's go back to the home screen, and we'll do a row reduction on a row reduction on matrix B. So we get that 1, 0, negative 3, 0, 1, 4, 0, 0, 0. Boy, we got very, very similar to what we had last time. All right, now again, what this means as a general solution, let's go to a Word document so we can write out the general solution. So we have 1, 0, negative 3, 0, 1, 4, and then 0, 0, 0. Okay, so as the general solution, we have x1 would be equal to a positive 3x3, x2, which would be equal to a negative 4x3, and an x3, which would be a free variable. All right, so if you let x3 be anything it wants to be, it's going to look like vectors 3, negative 4, 1 times any real number that we want. Notice in my previous problem what the null space was. The null space was 3, negative 4, 1 times any real number. So what we see is that even though these are two very different matrices, they actually have the same null space. Okay, so the matrices that we were dealt with in the previous problem and in this problem were two different matrices, but they did in fact have the same null space. All right. I want you to try one more matrix here. So I want you to find the null space of matrix A given this matrix. Push pause on the video and go ahead and try it. Now, the story here is that once you've done this, once you've created the augmented matrix, again, you don't have to write out the column of zeros, but once you've created the coefficient matrix or the augmented matrix and solved it, so we solve this homogeneous equation and we row reduce, this matrix actually row reduces to the identity. So the row reduced echelon form is the identity. Now think about what this means. This means that the general solution to this would have been that x1 has to be equal to 0, x2 has to be equal to 0, and x3 has to be equal to 0. So that means that the null space of A is actually just the set containing the 0 vector. So if we write this out, it's going to just be the set which contains the 0 vector. Now it's going to be in 3 dimensions, but that's the only thing the null space will contain. So if you remember, this was the trivial subspace of a vector space. So this null space is the trivial subspace. All right? Sorry, I can't scroll that. So there we go. The null space only contains the 0 vector. The null space of this matrix, anyways. Now, the column space, a little bit different. It's just the span of the columns. Okay? And if you think about it as some sort of analogy to that matrix equation, it's the set of all outputs of the matrix equation. So it's the set of all possible outputs. All right, no matter what the input is. Whoops, that should say from Rn. I apologize. There we go. So it's the set of all possible outputs after we get that. So the column space, it's the span of the vectors, and again, these vectors are supposed to represent the columns of A. So any linear combination of the columns of A is in the column space. The notation we use is COL of A for column space. Now, if A is an m by n matrix, then the column space is a subspace of Rm. Okay? Think of what the column space is. It's a bunch of linear combinations of vectors from the columns of A. Well, the columns of A have m rows. So when you add those things up, what we're going to get is still a vector with m entries. All right, so each of these A's have m entries. If you take linear combinations, they all have m entries. All right, so think about how we would prove this. If you think about this hard enough, what you'll see is there's a difficult way to prove this and an easy way to prove this. All right, the difficult way to prove this is to go back and try to say subspaces satisfy these 3 properties, and let's see if the column space satisfies these 3 properties, specifically 0 vectors in there, closed under addition, closed under scalar multiplication. The easy way is to remember back to something we talked about in 4.1, specifically this idea. In 4.1, back in 4.1, we saw that the span of any set of vectors is a subspace. Well, the column space is just the span of a bunch of vectors. So back in 4.1, we saw that the span was a subspace. We proved that. So I don't need to go ahead and prove again that. So all I have to do is say the column space is a span of vectors. Any span of vectors is a subspace of the Rn that I'm working in. And that's it. So that shows that that's enough to show that the column space is a subspace of Rm. Now, we're going to take the matrices that we dealt with last time, we're going to find the column space of those matrices. And once again, there's a number of ways we could show this. We could just, in fact, if we wanted to find the column space of this matrix, we can say it's the span of this vector, and this vector. But what we will see, or what we do see, when we row reduce, because we've already done this, is that when you row reduce, you end up with two pivot columns. And this third column can be written as a linear combination of these two. Okay? So all we have to do, we actually don't need this third column in some sense to get linear combinations of all three columns. So if I wanted a linear combination of 2, 1, 3, 1, 6, 1, I could have also accomplished that feat by taking a linear combination of 2, 1, and 3, 1. All right? So just to remind you of what I'm saying here, I'm looking for all possible B. So I row reduce my matrix A, I look at B, all kinds of good stuff could happen there. But when I'm thinking column space, I'm thinking of pivot columns. So the column space of A is going to just be the span of my first two vectors. And when I say first two vectors, I mean, whoops. Oh boy, this is not coming up there. I mean the first two vectors in my original matrix. So I'm saying the vector, in my case, if you remember the original matrix A, I'm getting a little bit low there. The original matrix A in the first column was 2, 1. And the second column of A was the column 3, 1. All right? So I don't need this third column to be thrown in because that third column is redundant. It's already a linear combination of the first two. So the column space of A is simply the span of these first two columns in my original A. Now again, notice I'm not using the column in the row reduced form. The row reduced form just tells me where the pivot positions are. So it tells me just the, quote, important columns, unquote. All right? So therefore, we just found the null space and the column space of that matrix. Now, what we can do is we can make now the following observation. Because our matrix was a 2 by 3 matrix, I want you to notice that the column space was a subset of R2, and the null space was a subset of R3, okay? So the null space had to have vectors with 3 entries because we had 3 columns. But the column space had to have vectors with 2 entries because we had 2 rows. So again, the column space is a subset of R2, and the null space is a subset of R3. Okay, so I'm just trying to make that observation be clear. All right, So the column space in this case, subset of R2. Null space is a subset of R3. It's a both are subspaces, not just subsets, but also subspaces. Okay. Now we can answer that question without even having to find the null space and the column space. So let's say we have a matrix like this. It has 3 rows and 4 columns. The column space is a subset of Rk for which value of k, and the null set is a subspace of Rk for which value of k. These will be different k's, possibly. I want you to take like 5 seconds and think through that and just ask yourself which value of k. Again, don't reduce, just ask yourself from based on what you know and based on the number of rows and the number of columns, what the k's have to be. All right, so column space has to be linear combinations of these vectors. These vectors have all 3 entries. So the column space is a subspace of R3. The null space, well, in order for it to be in a null space, this matrix has to multiply by the vector. And that means that the vector will have to have 4 entries in order to multiply by A. So the null space is a subspace of R4. So column space is a subspace of R3. Null space is a subspace of R4. Now, all of these matrix transformations were examples of linear transformations. Okay? And we can extend the idea of linear transformations to all vector spaces, not just Rn, but any vector space we can extend linear transformations to. And we want to do this now because they're always the matrices we saw, any linear transformation from Rm to Rn can be represented by a matrix. Okay. But we want to expand the idea now of linear transformations to be applied to any vector space. Okay. So it's just what we had before. A transformation from a vector space V into a vector space W is just a rule or a mapping which sends each vector from V to a vector in W. Moreover, so that's what a transformation is. To be linear, we have to satisfy these 2 properties. And the 2 properties are, well, our favorite ones. Does it preserve vector addition? And does it preserve scalar multiplication? All right, so if you add vectors on before you transform them, is it the same as if you transform the vectors and then add them? Preserving addition. Well, when you multiply by a scalar and then transform it, is it going to be the same as if you transform the vector and then multiply by the scalar? So do we preserve vector addition? Do we preserve scalar multiplication? If you do, then that transformation is linear. Okay? So let's try to show if or if not this transformation is linear. In fact, it is, but we'll show that this transformation is linear. Now what we're going to do is we're going to take polynomials, of degree 2 and less, so any polynomial of degree 2 or fewer, can be written as a real number plus a real number times x plus a real number times x squared. And we're going to map that into R2 by just taking my first entry of R2 to be the constant in my polynomial, and the second entry in R2 to be 3 multiplied times the coefficient of x squared. All right? So we're going to show that this transformation is in fact linear. So we take this mapping, and what we're going to do is see what this mapping does to arbitrary vectors. First off, let's talk about the sums. So let's see if we preserve vector summation. Okay? So what we do is we take and we create a U. Now, our U, yeah, I'm just going to write an arbitrary vector. That'll be our vector U. And we're going to add it to another arbitrary vector. I'll call it vector V. So scalar times x, scalar times x squared. All right? And then what we're going to do is we're going to see what this transformation does after we add it. So we're going to add and then transform it. And then we're going to do the same thing, but in the next example, or excuse me, in the next side, we're going to say, well, does that do the same thing when, that didn't work. I apologize for this. When I take t times the first vector and then add t times my second vector. I said times, I mean of my second vector. All right. Now, if this is a linear transformation, these two things should be equal. Adding things up and then transforming should be equal to transforming and then adding them up. Okay? So here's what we do. This first one. If you add things up, what's going to happen? We're going to get t of, and then notice what my constant numbers are. My constant numbers are going to be a0 plus b0. And then the coefficients, let me actually just write a little bit of a parentheses around there. So my constant number is going to be the sum of a0 plus b0. My coefficient on the x is going to be a1 plus b1. And then the coefficient on the x squared is going to be a2 plus b2. All right. Now again, this is just one big long vector. What the rule tells me to do is it tells me that my transformation is going to throw out 3 times the constant in the first spot. Or I mean, I'm sorry, just the constant number in the first spot, and then 3 times the coefficient of x squared in the second spot. So in the first spot, it's going to give me a0 plus b0. In the second spot, it's going to give me 3 times the coefficient of x squared. That's going to be a2 plus B2. So that's the vector I get out when I add, then transform. Now I'm just going to rewrite this vector just slightly. I'm going to distribute that 3 into the second entry. So it's going to be 3A2 plus 3B2. All right, because I kind of know what's going to come. So there you go. When you add first, then transform the result, you get this. What if we transform the result and then add? Well, what's going to happen? We're going to get a something from R2. It's going to have A0 in the first entry, 3 times A2 in the second entry. Then we're going to get another vector over here, which is going to have B0 in the first entry, 3 times B2 in the second entry. So let me just write that down. And it's pretty clear to see that we are, in fact, going to get the exact same vector that we got earlier. We're going to end up with an A0 plus 0, A0 plus B0 in the first entry. And the second entry is going to be 3A2 plus 3B2. Now, all this shows is that when you take two arbitrary vectors, the transformation of them after they've been added is the same as if you transform them and then add the results. So the adding property works. In other words, we preserve sums. Now let's check to see that we preserve scalar multiplications. All right, so we go here, we're going to check. And obviously what we're going to be doing is we're trying to check if t scalar u for an arbitrary vector u is the same thing as if you take the scalar after you've transformed. Okay? So in this example, let's do the same thing. I will go up and get that. So in this example, what we're going to do is take t times my vector after I've taken take scalar multiple of an arbitrary vector and then hit it with t. And then I'm going to check and see if that's the same thing as if I hit the vector with t, transformed it, and then applied the scalar multiple. Now in the first case, what we end up with, I can distribute that c into every single term of my vector. Then transform it. When you transform it, it's the same concept that we've always gotten in this example. So we transform it. First entry would be c times a0 Second entry would be 3 times the coefficient of x squared. And that would be what would happen if I took my transformation after I multiplied by a scalar. Now in this case, let's do the opposite angle. Let's take my transformation. Well, if I transform the vector first, what we end up with is just a sub 0, 3, a 2. And it's pretty easy to see that this is in fact the exact same vector that we had earlier. So it's the CA0. Oops. Typing bad today. All right. So C A sub 0 and then 3 C A sub 2. I am using a little bit of commutative property between 3 and any scalar, but that's pretty straightforward. So we see that we preserve scalar multiplications and we preserve sums. Therefore, this transformation, which maps a polynomial onto R2, is a linear transformation from a vector space into another vector space. All right, so this transformation is, in fact, linear. Now, notice what I did in this transformation. I was kind of dealing with the coefficients here. You can imagine that if you did this in general, coefficients should be linear combinations over here. But I won't get into that right now. This example is a linear transformation. Now I want you to push pause on the video and see for yourself if this transformation is linear. We're going to go polynomials of degree 2 and less, but I'm going to think of them as functions. And what we do is we take a polynomial, we put it into this transformation, and we're going to spit out R3. Now how we do that is we're going to see whatever value the polynomial is when I plug in 2. That's going to go in my first entry. In the second entry, we're going to have a value of the polynomial when you plug in 0. And in the third entry, you're going to have another polynomial value when you plug in 2. So push pause and see if you can determine whether this is a linear transformation or not. Okay. All right, so let's think of this transformation, see if we can show that it's linear. All right, now first off, let me just, if you haven't quite got this yet, haven't quite got the concept yet, what we're going to do is we're using function notation. For instance, we have a polynomial. Let's take an arbitrary polynomial of degree 2 or less. So let's take x squared minus 3x plus 4. Okay? So what this transformation is doing is it would take that polynomial and it would plug in 2. Now, when I plug in 2 into this polynomial, what we're going to get is 2 squared minus 3 times 2 plus 4. And whatever that comes out to, that's going to be my first entry. Then I'm going to plug in 0. Oops. So I'm going to go 0 squared minus 3 times 0 plus 4. That'll be my second entry. And my third entry is just going to be plug in 2 again. There we go. All right. So the vector you're getting out is the vector from R3, which in this case, let me think about what that is. I believe you get out at 2 that way. Oh, that was a bad choice probably, but 2 squared is 4 minus 6 plus 4 is 2. This entry is a 4. This entry is a 2. All right. There we go. So that's what's happening. And if you change your polynomial, let's say we change it, I'll change it slightly to something, instead of having plus 4 at the end, let's say we had plus 9 at the end. All you would have done is plugged in everything into that polynomial. And then all of a sudden you get vector output, which is 7, 9, 7. Okay, so that's what this transformation is doing. Now let's see if this transformation preserves addition and preserves scalar multiplication. Okay, so what we're going to do, let's do preserving sums first. It's going to look very similar to what we just did. Whoops. We're going to look and see what's going to happen when you transform a sum we'll say of one polynomial plus another polynomial. If we get the same thing as if you transform the one and then add transforming the other. Okay? Well, if you transform this, what you're going to get out, oops. Well, what's happening here? We have to plug in 2, plug in 0, then plug in 2. So we're going to plug in, we're going to add the two polynomials, plug in 2 to the sum. Now, if you plug in 2 to the sum of a polynomial, that's just like plugging in 2 to the first one and then plugging in 2 to the second one. Hopefully, we all know that's what happens. Plugging in 2 into a function, which is a result of two functions being added, is like plugging into each of them. Same thing with 0. Plug in 1, plug into the other, both 0. And then again, we plug in 2, plug in 2, and there we go. Now it's pretty easy to see that this is going to be the same thing as what we get when we take a polynomial, transform it, and then add the other polynomial transformed. Okay, all we end up with, whoops, well, that skipped, is that first polynomial transformed. What we do, so transform the first polynomial, plug in 2, plug in 0, plug in 2 again, and then add that second polynomial transformed plug in 2, plug in 0, plug in 2 again. All right? And in fact, when you add these, you do in fact get the exact same vector you got up here. All right? So adding those gives you the exact same vector that we got up there. I don't like that. So what we see is that we preserve sums. Now let's think about scalar multiplications. So what we're going to do is we're going to take a scalar and we're going to multiply it times a polynomial and then transform it. And then we're going to take the scalar outside of the transformation of the polynomial. Now, if you transform the scalar times a polynomial, all you're going to do is plug in 2. Now, what's the result here? Well, if I plug in 2, it's just scalar times plugging in 2. What's the result in the next one? Well, it's just scalar times plugging in 0. What's the result in the last entry? It's going to be a scalar times plugging in 2 again. So there we go. That's the result of taking the transformation after we've multiplied by a constant. Now, if we multiply by a constant after we do the transformation, we take a constant times a vector. Well, after we do the transformation, what's the transformation? The transformation is this one. So we take scalar, multiply it times that vector, and sure enough, that scalar is just going to multiply n times each piece. Scalar times polynomial, scalar times polynomial, scalar times polynomial, times the resulting number. So sure enough, this preserves scalar multiplication too. So since we preserve addition, since we preserve scalar multiplication, this transformation is in fact linear. Okay, so we see an interesting linear one here where we deal with coefficients of polynomials. We see another different type of transformation here where we plug in numbers into polynomials, but they're both from polynomials to Rn. Let's do another one from a different vector space. This one is going to be from the vector space of differentiable functions, so functions which have a derivative. So specifically, they're going to have derivatives, and they're going to have continuous differential derivatives on some interval from a to b. So in other words, we're going to look at functions which have nice derivatives over some interval. And our operator is going to take such a function and just spit out the derivative. And we want to show that t is linear. So what we need to do is show that the taking of derivatives preserves addition and preserves scalar multiplication. Now, this one is pretty easy because hopefully we all know what the derivative function does. Let's go back up. Whoops. Thought that was weird. Okay. Whoops. Let's go grab this. So my mapping is taking a function to its derivative. And we're assuming, that's why I said nice continuous differentiable functions. I'm assuming that all these functions are really nice and that the derivative always exists. Okay, so let's see if it preserves addition. If I take f plus g and I take the derivative of f plus g, we know that the derivative of f plus g does distribute over addition. So if I take the derivative with respect to x of f plus g, you do get f prime plus g prime. Okay? Which in fact is pretty obviously the same thing as what you would get if you took the derivative of f and then took the derivative of g. All right, so there you go. So we do preserve addition. Now, does a derivative preserve scalar multiplication? Well, yes, we know it does. So if we take a scalar times a function and we want to find the derivative, that's the same thing as a scalar times f prime. And obviously, that is going to be the same as scalar times the transformation. So scalar times f prime in both cases, right? So the derivative operator preserves function addition and preserves scalar multiplication. So the derivative operator is a linear transformation on the set of differentiable functions. Okay? Now, we've dealt with some matrix transformations, and we looked at the column space and the null space. That was the span of the vectors and the vectors which are sent to 0. Well, there's an analogous idea when I go out to any linear transformations, and that's kernel and range. Kernel is the set of all vectors that get mapped to the 0 vector. Range is the set of all output vectors. So kernel and range are my analogous things. Kernel is kind of like the null space of a matrix. In fact, if a transformation is a matrix transformation, it's going to be the null space of the matrix. Range is like the column space. And if the linear transformation is a matrix transformation, they're the same. Okay, so if we're on Rn, kernel is the same as the null space, range is the same as the column space. But if we're not on Rn, then it pays to have these different linguistics, kernel and range. So let's take a moment to just think about what the kernel and range were for example 1. Okay. Now, we're not going to do like hardcore proofs or anything or things like that. I just want you to think through what would have gotten mapped to the zero vector. Well, in order for us to get mapped to the zero vector, the first entry would have had to have been 0. That means this constant would have had to have been 0. And also the second entry would have had to have been 0. That means the coefficient on x squared would have had to have been 0. Let me do this in the Word document. What I'm saying here is we have this transformation that sends a polynomial of degree 2 to a0, a2, yet we want to see what the kernel is, so we're asking which polynomials are going to be sent to 0, 0. In order to be sent to 0, 0, it's pretty clear that the a0 has to be equal to 0, and the a2 also has to be equal to 0. So the kernel of this transformation is all polynomials of the form, well, what form would it have to take? Well, the a0 would have to be 0. The a2 would have to be 0 as well. Notice a1 could be anything it wants to be. All right, so kernel is any polynomial of the form 0. Whoops, let me go this way. Hopefully we preserve, yep. 0 plus a1x plus a2, which has to be 0, times x squared. So it's all polynomials of the form that it's just a constant times x. And if you were writing this in set notation, it'd be the set of all things that look like a constant times x, where this could be any real number. This a1 could be any real number. All right? So that's the kernel of that transformation. Now, let's think about the range of this transformation. Well, the range of this transformation has to deal with the outputs. What outputs are possible? The range of this transformation, well, a0 can be any number we want, and a2 can be any number we want. So the range of this transformation is quite simply any number we want. I'll just put a for any number we want in the first entry, and any number we want in the second entry. So the range is essentially all of R2. My first entry could be any real number. My second entry could be any real number. So the range in this case is all of R2. Okay. Another way to write that would be to write the span of the elementary vectors from R2. You can write that in a number of different ways. Okay? So the kernel is all polynomials that look like this. The range is all vectors that look like this. Okay? What I mean by the thing I just said was that you could write AB as any linear combination of the standard basis vectors for R2. Okay. Again, if you remember that from R there. So any linear combination of the standard basis vectors from R2 is in the range, and that means that the range is the entirety of R2. Now I want you to look at the next idea here. The next example we had was where we plugged in numbers into our polynomials, p of 2, p of 0, p of 2. I want you to think through what the kernel would look like here and what the range would look like here. Push pause, see if you can think through this. This one's a little trickier. All right, so let's go to the Word document and think through this. Well, let's take the kernel first. Now, if we're going to look for the kernel, we want our output vector to be the 0 vector. Now, what this means is that if you plug in 2 into your polynomial, you should end up with a 0. And if you plug in 0 into your polynomial, you should also end up with a 0. This third entry, plugging in 2 and getting a 0, is redundant with the first, so I just have to write p of 2 equals 0 once. Now, if you think about what that means, p of 2 equaling 0. Well, p of 2 equaling 0 means that the polynomial is going to have a factor of x plus 2. Because when you plug in two into the x plus 2, that's how you get a 0. And moreover, we can't just have a factor of x minus 2 because the x minus 2 by itself would not satisfy over here. So we need a factor of just x. All right? Because if you have a factor of x, you plug in 0 into that, and you get a 0. Now, if it has to have a factor of x and a factor of x minus 2, then it needs to be your polynomial is going to have to be some multiple of x times x minus 2. All right? Now, you can notice that this is a second degree polynomial. So when we talk about multiples of this, we can't multiply by any other factors with x in it, or we go up to a third degree. So what I'm claiming is that all polynomials that give me the 0 vector are just scalar multiples of this one. So the kernel is all vectors of the form a scalar multiple multiplied times x squared minus 2x. All right? You could distribute that c in if you wanted to, but that's it. So the kernel is all vectors of that form. Hopefully that makes sense. That we needed a factor of x and a factor of x minus 2 to make both these things 0. Okay, let's think range. So let's think range. Why that keeps doing that. So we have our transformation. Now, the nice thing about these polynomials is that if you think about it, what do we want to accomplish here? We want to accomplish something. We're going to get a real number in our first, second, and third entry. Notice that our first and third entry are going to be the same. So what I'm trying to argue is that no matter what real number you want, I can find a polynomial that when you plug in 2, you get that specific real number. Now, that's going to be the same as the third entry over here. So no matter what number you want, I can find a polynomial that when you plug in 2, you get that number. Moreover, I can also find a polynomial such that when you plug in 0, you get any other number you choose. Again, that's a pretty easy task to accomplish. That's nothing earth-shattering. So notice that your range is going to be all vectors of this form. So your range is going to be all vectors of that form. If you wanted to write this as a linear combination of two vectors, you could write it as A times 1, 0, 1 plus B multiplied times 0, 1, 0. Okay? So all vectors of this form or this parametric form, that's your range. So there you go. So the range is pretty straightforward. Kernel of this one's a little bit tougher because we have to understand that in order to get 0, your polynomial has to have a factor of x minus 2. In order to get 0, your polynomial has to have a factor of x. Range is a little bit more straightforward. All right. I want you to try one last one where you find the kernel and range. And this is the derivative operator. So think of the set of continuous differential functions which have continuous differentiable derivatives. And think about what the range would be, what the kernel would be. All right, so hopefully you went ahead and pushed pause and did that. If you haven't, do it now because we're going to go through solving. All right, we're going to go back to that Word document. We're going to look for the range. We're going to look for the kernel. Let's look for the kernel first. I think this will be fairly straightforward. So we're going to look for the kernel first. All right, now it's the derivative operator. So the kernel, remember, is the set of all things that get sent to 0. Now the 0 function is just 0, okay? So the kernel is going to be all functions with derivative of 0. Now we know those functions better as constant functions. All right? So the kernel is the set of all constant functions. All right, specifically, if we were going to write this out, it's the set of all functions which look like f of x equals, let's say, b, such that b is a real number. Okay, so it's things like f of x equals to 7, f of x equals to 8, f of x is equal to 92, or negative 16. If you take the derivative of a constant number, you get 0, and so the kernel is the set of all constant functions. All right. By the way, just as a note, constant functions are the only ones which have derivative of 0 everywhere. So that's the idea. Now, what about the range? So let's go through the range. If I take a function and take the derivative, what types of functions are going to be the derivatives? Well, this was actually explained in the problem. It says we want differentiable functions with continuous differentiable derivatives. So what that simply means is that these derivatives will be continuous and differentiable. So the range is the set of all functions with continuous differentiable the set of all functions which are continuous and differentiable. Okay, so it's all the set. We wanted to have continuous differentiable derivatives in our original set, so that's it. Okay, so it's a set of all, think continuous nice functions. So hopefully that all makes sense. Again, it's really hard to describe all those functions because we have all polynomials, sine functions, cosine functions, all kinds of other functions, exponential functions. All of those types of functions have continuous and differentiable derivatives. So that's the ideas that are in section 4.2. Next time, we'll start section 4.3. Hopefully, well, that will be slightly smaller of a section.